Welcome back, children. In the previous video, we talked about the magnetic dipole moment. We said if a current is flowing in a loop, then it is going to behave like a magnetic dipole. And if it behaves like a magnetic dipole, then you can calculate the magnetic dipole moment of that magnetic dipole. And it was given by this expression, M, which is a magnetic dipole moment, is equal to NAI. N is a number of turns, the closely wound turns of the coil, and A is the area of that loop, and I is the current flowing through it. Okay? This leads us to think of an electron moving around the nucleus of an atom as a magnetic dipole. Why? Electron is moving, which means electric charge is moving. Electric charge moving means that there is current, and if there is current, then there would be a magnetic field. And if the current is in a loop, then there would be a magnetic dipole. Then if there is a magnetic dipole, then there should be a magnetic dipole moment which you can calculate. And that is what we are going to do now. So let me take an atom. This is the nucleus of an atom. Okay, so Z into E, positive. And let's take an electron which is revolving around this nucleus. So here is the electron. Let me choose this direction. It goes like that. Okay. This is the direction of the electron. This is E. It's minus. Okay. This is plus. That's minus. Okay. So the electron is moving in this direction. Let's suppose that this is the radius of the circle, and V is the speed or the velocity, okay, with which the electron is moving around this circle. So since the electron is moving this way, the current should be in the opposite direction. So this is the direction of the current I. The electron is moving this way, so that the current must be considered to have taken this direction. Okay. Now what should I do? I want to find the magnetic moment of this. Okay, current is moving in this direction. Okay. So clearly, what is the direction of the magnetic dipole moment? I said I'm going to use the right hand rule. So thumb is going to point in the direction of motion, the current. So you see, then it goes like that. If I curl my fingers, then it goes like that. So it's into the board. So the direction of the magnetic moment, if I take M, then the direction of it is into the board. So into the board. Okay. Okay, what is M? The magnitude of M is equal to NAI. But what is N? It has only one turn, in the sense like there are not many turns, just a one turn coil. It's like a single loop. Okay. So this is, N is going to be 1. N is going to be 1. And A is pi r squared with the area of the loop. It's pi r squared, and then I. That's the magnetic moment. But what is I here? Okay, this is a charge. E is a charge, and it moves with a velocity v or speed v, let me say. Then I should be able to calculate the current. So what is current? Current is simply I is equal to charge per time it takes. So the charge here is E, and then I need to find the time it takes to make this round. So v is this speed and 2 pi r is the length. Then I can find the time it takes to cover this. So the time it takes to cover this would be E and T, and take capital T. It's better. The time period for one station. So this is T is equal to, it's going to be 2 pi r by v. So it's going to be 2 pi r by v, speed. So v is the speed, 2 pi r is the length it's going to cover. So how much time it would take to cover, and this is the time. So the electron is here. After some time the electron is going to come here. Then sometime the electron is going to come here. Then come here, come here, come here. So now I can calculate in 1 second how many charges would cross this this point. So I is equal to E by T. So I is equal to E by 2 pi r by V, then V will come here. So this is the current. Okay, so now can I calculate the magnetic moment? Yes. M is equal to pi r square into EV by 2 pi r. So pi and pi will cancel, r will cancel with r square. Then I am going to get M is equal to EVR by 2. So that's the magnitude of the magnetic moment. The direction, as I said a little while ago, is into the bore. So this is into the bore. But I get this expression, it's all right. But if we need to calculate M, then I need to know the velocity of the electron and also the radius of the electron. That's going to be a little difficult, right? So can I find an alternative way to do this without having to know the velocity and the radius? Well, we know that the Bohr's atom model relates the angular momentum to nh by 2 pi. So what is the angular momentum? The angular momentum L, let's say I will do it here. This angular momentum L is equal to mv to r. I've got VR here. So if I multiply and divide this expression by the mass of the electron, then I will get the angular momentum of the electron, the magnitude of the angular momentum of the electron, as part of this expression. And if I know the angular momentum, then I can relate it to the Bohr's postulate, which says that the angular momentum is equal to nh by 2 pi, and I can kind of eliminate the need to calculate, or to need to know the value of V and R this way. Let's see what we can do now. Okay. We also know that this L is equal to nh by 2 pi. Okay, so with this background, we are coming here. So this is magnetic moment. Okay, this is equal to E, V, R. Now I am going to multiply this with the mass of the electron and divide with the mass of the electron. Okay, so this is ME, M subscript E. Okay, so it's not M into E, it's ME. E is here, E is a different quantity here, this is the mass of the electron. Okay, so this term M or V can be taken to be L. So this gives me 2L by L EL by 2 ME. So this is actually the magnetic moment now. But what do we know? We know that L is equal to nh by 2 pi. If we take the first orbit, then n will become 1, then L will become h by 2 pi. The first orbit, M is equal to E. Instead of L, I'm going to use NH, it's going to be 1 into H, 1 into H by 2 pi divided by 2 ME. So, if I multiply this, then the magnetic moment is equal to HE by 4 pi ME. Well, H you know, E you know, 4 is a constant, pi is a constant, mass of the electron also you know. Now you can find the magnetic moment of the electron of the first orbit. Likewise, you can do it for any orbit. Okay? So, if I plug in the numbers, so M is equal to H is 6.6 into 10 to the power minus 34 into E is the charge value 1.6 into 10 to the power minus 19, so divided by 4 into 3.14 into mass of the electrons 9.1 into 10 to the power minus 31 G, and that is going to give me this for 9.27 into 10 to the power minus 24 ampere meter square. So that's my okay. So I can calculate the magnetic dipole moment of an electron revolving around the nucleus of an atom this way. And this number is called as the Bohr magneton. So the Bohr magneton. Well, another thing is that in addition to this dipole magnetic dipole moment that the electron has, this 9.2 10 to the power minus 24, in addition to this, it also has a spin magnetic moment. The electron, it's not that it's spinning around its axis or something, but it's left to the quantum mechanics part of it to explain. It's not part of your syllabus, so we are going to skip it now. But I want you to remember that in addition to this magnetic moment, an electron will also have a spin magnetic moment, which is also equal to this 9.27 10 to the power minus 24. So that's the background information. Okay. But the main thing here is that you can calculate the magnetic dipole moment of a revolving electron. As I said, a moving charge constitutes a current, and if it moves in a loop, then the current is in a loop. If the current is in a loop, then the loop is going to behave like a magnetic dipole, and if it behaves like a magnetic dipole, then you can calculate the magnetic dipole moment, and that is what we have done here. I hope this is clear to you. Okay, now let's put all our knowledge into some use. We are going to construct an instrument we call as the moving coil galvanometer. So this instrument can be used to measure the current and the voltage in a circuit. Slight adjustments, we'll talk about that a little later. But the basic construction of the instrument, the moving coil, the coil galvanometer, is going to be done like this. This instrument will have a permanent magnet, okay? Like it's in the shape of a circle, if you see, to maintain the field at a constant value. So it is in the shape of a circle, and you have a soft iron core, okay, just a soft iron core on which you have your coil wound around that soft iron core. Well, you use soft iron because if you keep hard iron in the presence of a magnetic field, then it will easily get, it can get magnetized and it won't lose the magnetism. So particularly if you are using a coil, the coil will have magnetic field, and that can magnetize that magnetized iron. So you are going to use soft iron core, which means that it won't retain the magnetic field once the current is switched off, or it will retain only a very small amount of magnetic field. So that's the reason you are going to use soft iron for all your electrical equipments, measuring equipments, and all the other places too. So you have a soft iron core and you have a winding, the coil wound around that. So you have a permanent magnet, a soft iron core, and then a coil wound around that. You are going to pass current through that coil. So what is going to happen now? You are keeping a coil which is carrying current in the presence of a magnetic field. So that coil is going to experience a torque now, both sides. It will experience forces, so you will experience a torque. So this coil is going to turn. If you don't do anything else, then what will happen is, as we discussed in the previous video, this coil will keep oscillating. Okay, you don't need that. So what you need is how much it deflects. So that can be found by using a spring, a spiral spring that is connected to the soft iron core and then to the bottom, the body of the meter. So when the coil tries to turn, then this spring will pull it back. It's a torsional spring. It's not a linear spring. It's a torsional spring. It's more like a mosquito coil. Okay, it's like that. So when you're trying to pull one side or one end of the coil, then it's going to tighten. If you can notice, it will try to oppose that motion. So as this tries to move, then the coil will try to pull it back. So at some point, the torque of that coil and then the torque produced by this magnetic field on this current carrying coil, the torque on the spring and the torque on the coil would match. Then it will come to an equilibrium condition. So it will just deflect, and then as it keeps deflecting, it keeps pulling, the spring keeps pulling the coil, and then at some point it's going to be equal. So the torque on the coil and the torque on the spring would be this. So then it will stop. Okay, so now you can find the deflection. If you pass more current through the coil, then the coil will experience a greater torque, so it will try to go further, but then this spring, the torsional spring, will try to pull it back. As it tries to pull it back, and you will find another equilibrium position. So depending on the current that is flowing through the coil, it is the torque experienced by the coil would be different, as you know, and it's going to be balanced by the torque from this spring. So at some point they will reach equilibrium and it will stop. Okay. You are going to see the deflection too. So you have the pointer at the null position here. When there is no current flowing through it, then the pointer will point here. Then as it moves, then the pointer will move in this direction. Then it will stop at some place. Then you can read. So this is a basic structure. Okay. Now let's see how to calculate the current, okay, that's flowing through the coil. What is the relationship between this deflection and the current flowing through the coil? And that is what we would see now. Okay, so the condition for this is that the torque produced by this magnetic field on the coil must be balanced by the spring that you are attaching to the coil and the body. So it won't allow you to move too much. So this torque on the coil, I call it as tau C, is equal to mB. This we know. What does this M? M is magnetic moment. Okay, what is the magnetic moment of this coil? So it is, as we've seen already, it is NAI. So N is the number of turns in the coil, and then A is the area of the coil. You are seeing it from the top here. So NA and then I. I is the current through the coil. Into B. B is the strength of the magnetic field of the permanent magnet. Now, what's the torque on the spring? So that I will call this 2S. So that's going to be on the spring. The spring constant K. This is a torsional spring constant. Okay, I told you the spring is more like a mosquito coil. Okay, so as you pull the one end, then it's going to tighten. Okay? It's like that. So this is not a linear spring that you have come across before, right? So yes, it's going to Kx, but now it depends on the angle. So K is phi. Let's see angle. So this is the torsional spring constant, and phi is the angle of deflection. Normal spring, the linear spring, will give you Kx. That is the spring constant K multiplied by the distance x. Here the equivalent of distance is the angle. So this is a torsional spring. Okay, so K. Like this, like a mosquito coil. So these two must be equal. So which means that K phi is equal to N A I B. So phi can be calculated as N A B by K into I. So this is a relationship between phi and I. You see, N is the number of turns. So once you designed this instrument, the number of turns cannot be changed. Then A, the area of the coil, that also cannot be changed once you have the instrument in your hand. So you cannot arbitrarily change the area. So that's fixed. Then B, the magnetic field, again that cannot be changed because they're permanent magnets. Okay, you cannot pass current and then change the magnetic field strength here. Okay, they're permanent magnets. So B cannot be changed. K, again the spring constant. So that also cannot be changed. So none of these quantities can be changed. So this is all these quantities in the brackets are constants. So you know then that phi has a linear relationship with I. So as the current increases, the angle will increase linearly. So for 1 ampere it is 10 degrees, and for 2 amperes it will be 20 degrees, and for 3 amperes it will be 30 degrees. So the angle will change linearly with the current. So this is going to be linear scale. So this is how the moving coil galvanometer functions. So you send current through the coil. Okay. Maybe you have a battery or something. You send current through the coil, and then you're keeping the coil in the magnetic field. Now it's going to deflect, so it's going to experience a torque as we discussed before. And now you are going to use a torsional spring to pull it back. Okay, you don't allow it to do these oscillations that we talked about yesterday. If there is no spring constant, then it will keep oscillating, as you said. Okay, now it won't do that, because as it tries to move, then you're trying to hold it, you're pulling it. Okay, now we will talk about what is called as the current sensitivity of the moving coil galvanometer. We know this expression, we derived it. Phi is equal to NAB by K to I. So phi is the angle of deflection and I is the current flowing through the coil. We also said that phi, the angle of deflection of the galvanometer, is proportional to I. We said that. So if the current increases in the galvanometer, then the deflection will be more. So this is measured in degrees or radians, and this will be in amperes. Okay, so you have this expression. So the current sensitivity is how many degrees or radians does the galvanometer deflect for a unit current. So that is called as the current sensitivity of the galvanometer. So how do I do that then? So this is how many degrees per unit current. So this is called as the current sensitivity. From this equation, I will get phi by I is equal to NAB by K. So how can you increase the current sensitivity? So what is it? Let's try to understand this a little more. The current, for a particular amount of current, the galvanometer can deflect say 10 degrees or 20 degrees or 30 degrees, 40 degrees. If it deflects more, then we say for a particular amount of current, the current doesn't change. Okay? I have 3 galvanometers. One galvanometer deflects, I send a certain amount of current, say 10 microamperes or something. Then the first galvanometer deflects to a certain angle, and then the second galvanometer deflects to a different angle. So the first one could be 10 degrees, second one could be 20 degrees for the same 10 microamperes. And the third one could be 30 degrees for the same 10 microamperes. Which is more sensitive to the same current, or which is the most sensitive to the same current? Clearly, the one which deflects 30 degrees is the most sensitive of all the 3. Because you are sending the same amount of current, but the deflection is more. So the precision could be more. If the deflection is less, then the precision will be less. If the deflection is more, then the precision of the instrument will be more. So the third instrument, which deflects 30 degrees, is considered to be the most current sensitive galvanometer. Okay? So if you want to increase the current sensitivity, then this is what you need to do. Well, you can either increase the number of turns in the coil. Then angle will, this term will become bigger. Okay? This number, this quantity will become a bigger quantity actually. Or you can increase the area of the coil. Or you can increase the strength of the magnetic field. You can have more powerful permanent magnets in the galvanometer. Or you can use a weaker spring, because the spring is providing the counterbalancing torque. We saw that. So if you have a weaker spring, then it will deflect more. If you have a stronger spring, then it will deflect less. So by controlling all these factors, you can increase or decrease the current sensitivity of the galvanometer. Okay. Okay, so there is clearly, once we talk about current sensitivity, then there can be another quantity called the voltage sensitivity, right? So I've talked about the current. If you have a galvanometer, here, okay. So if you send a certain amount of current through that, then it's going to deflect. Again, the question could be, clearly you would connect it to your battery, right? So battery, right? So that would send the current. I'm just saying, like there would be some amount of a voltage drop across the galvanometer, because the galvanometer will have a resistance, so which I call as RG, and then if you connect a battery V across that, then the voltage drop Ig into Rg should be equal to V. So the current through the galvanometer multiplied by the resistance will give you the voltage across the galvanometer. So for that voltage, how much does the galvanometer deflect? Same, current sensitivity, when current flows, the galvanometer deflects. As current flows, there is also a voltage drop across the galvanometer. If there is a voltage drop across the galvanometer, then you can find the voltage sensitivity too, along with the current sensitivity of the galvanometer. So how do we do that? Okay, then the current sensitivity, the voltage sensitivity will be the voltage sensitivity is the deflection of the galvanometer per volt, per unit voltage, and that is the voltage sensitivity. Okay, then can I get this from here? Yeah, I can. You see, this V, the voltage across the galvanometer, is given by I into the resistance of the galvanometer. So I can write this as phi by I into R G, the galvanometer. Okay, but you know what phi by I is, right? It's NAB by K. So this is given by NAB by K into Rg. Okay. So this is a voltage sensitivity. Now you have an extra term Rg there. Okay. Think about it this way. If you want to increase the voltage sensitivity, then I need to clearly use a low resistance coil. Okay, and I can also use a low resistance spring. Spring of weaker strength. Okay, I can use that, and I can also increase the strength of the magnetic field. I can do that. But what about these two things, N and A? N and A. Well, if I increase the number of turns, then I am increasing the length of the conductor. If I increase the length of the conductor, this resistance, the resistance of the coil, will not remain the same. So this will also increase. If we increase the number of turns, this will also increase. So it may probably result in reduced current sensitivity also, or even if it increases current sensitivity, it is not going to, if it increases, okay, let me take it back. But let's look at these two quantities, N and A. If I increase the number of turns, then the length of the conductor increases. If the length of the conductor increases, then the resistance of the galvanometer also increases. So if this increases, Rg can also increase. It depends on how much Rg increases as you increase N. So your voltage sensitivity may suffer. We know this. If I increase the number of turns, the current sensitivity will increase because there is no resistance component there. But the voltage sensitivity need not increase. It may even decrease. Or even if it increases, it need not increase in the same proportion, because as this increases, then Rg also increases. If the increment of Rg is smaller compared to the increment of the number of turns, then the voltage sensitivity will increase, but not proportionally, because this doesn't remain constant. As this increases, this also increases. So there is it need not be a straight line increment. In some cases it can even decrease, because you increase the number of turns, you are increasing the resistance. Then as you increase the resistance, the voltage sensitivity will come down. If this increases more than this, then this will come down. Okay. So while you improve the current sensitivity, by increasing the number of turns, you can never be certain that the increase in number of turns will increase the voltage sensitivity. This is something that you need to understand. And the same thing is true for the area. Well, if the area increases, what would you do? You may probably end up having a longer conductor, right? As area increases. So, if you have a longer conductor, then whatever argument that we had for the number of turns will be applicable to A also. So, if there is an increment in area, there will be an increment in the length of the conductor, for the most part, okay? Unless you change the structure. Okay? You're converting a square coil into a circular coil or something. Okay? Then you may increase the area, but even that has a limitation. But without increasing the conductor length, but even that has some limitations. Okay, but the idea is that in the normal sense, if you increase the area, you will increase the length of the conductor also. If the length of the conductor increases, then the resistance will also increase. So the voltage sensitivity need not increase. If the increment is proportional, then even after you have increased your area, this may remain the same. The voltage sensitivity may remain the same. Or it may increase, but not proportionally. Or it may even decrease, depending on what kind of material you are using for the coil. So this is something that you have to understand. So increasing current sensitivity need not necessarily increase the voltage sensitivity, particularly when you tweak with N and A. If you handle B and K, yes, it may increase. Definitely it will increase, because you are not touching the coil. So R is not going to change. So this will remain constant, these two things remain constant. So as you change, then it can be a proportional increment you can find. Okay. Hope this is clear. So we talked about current sensitivity and also voltage sensitivity. And we know that increment in current sensitivity need not necessarily result in voltage sensitivity. Increase the number of turns will increase the current sensitivity, but that need not result in voltage sensitivity. It may, but that's not certain. It depends on other factors too. It depends on the resistance of the coil. Hope this is clear to you.